We'd like to examine the motion of two particles. Here's particle 1, and here's particle 2. And each particle can have some motion. In between them is the center of mass. And what we'd like to do is figure out how to describe the motion of each of these particles with respect to the center of mass. So let's choose some coordinate system. Origin down here. Here's our particle R1. Here's our particle R2. And here is our center of mass. Now, in the reference frame of the center of mass, we have position vector R1 prime, and we have position vector R2 prime. And what we'd like to do is find expressions for R1 prime and R2 prime in terms of the positions of R1 and R2. Now, recall that the position of the center of mass for this two-body problem is given by m1 R1 plus m2 R2 divided by the total mass. And here we use the vector triangle that R1 prime equals R1 minus R center of mass. Now remember, this vector is equal to this vector minus that vector. Sometimes people like to say the vector R1 is equal to R plus R prime, and that's how we get that relationship. Now we can use our result here, that R1 prime is R1 minus M1 R1 plus M2 R2 divided by M1 plus M2. And when we combine terms, let's just do this so you can see it. R1 minus M1 R1 plus M2 R2 divided by the total mass. We now have the M1 R1 terms cancel, and we have a common M2 over M1 plus M2 times R1 minus R2. Now, R1 minus R2 is a vector that goes from here's R1, here's R2. So the vector R1 minus R2 is the relative position of vector 1 with respect to 2. And let's give that a special name. We'll call that R12, the relative position vector. So we have M2 over M1 plus M2 R12 is R1 prime. Now, you can easily see that if you interchange the indices 1 and 2, the only thing that changes here is a sign. And if we interchange 1 and 2, and this is an exercise that you can do, then R2 prime is minus M1. I'm interchanging the indices. The minus sign came from the interchange of 1 and 2. And so we get M1 over M1 plus M2 with the minus sign R12. Now, what is the significance of this result? If you know the position of R1 and R2, you know the relative velocity. If you have information about this relative position, if you know the relative position vector, then you can separately get the locations of the two objects in their center of mass frame. Now, this quantity in here will appear often, and I'd like to introduce a new quantity called the reduced mass. And that reduced mass, mu, is the product of M1, M2 over M1 plus M2. It's a simple exercise to see that 1 over mu is 1 over M1 plus 1 over M2, and we'll encounter that a little bit later. Then I can write both of these vectors, and this is our conclusion, that R1 prime is the reduced mass. Notice we have an M2 here, so we have to divide by M1 times the vector R12, and R2 prime is minus the reduced mass. Again, we now have to divide by M2, and you see this nice symmetry of M1 and 1, 2 and 2, R12, and that's our key result. When we analyzed a one-dimensional elastic collision in any frame, and we had a velocity v1 initial and v2 initial, that we saw that we could reduce, this is a one-dimensional elastic collision, we could reduce our, we always have the energy condition and the momentum condition, but when we combine the energy and momentum together, we found the following idea, that the relative velocity v12 which we called the relative velocity initial, was just equal to the final relative velocity. The statement there was that v1 initial minus v2 initial is equal to minus v1 final minus v2 final. And we called this the energy momentum relation for our classical mechanics. And then we could combine that with our conservation of energy law, conservation of momentum. And we've got a linear system of equations that is much easier to solve than the quadratic system. Now what I'd like to show is that this concept of relative velocity, that the v12 relative velocity is independent of the choice of reference frame. And so if we want to analyze a collision in any other reference frame, then we always can keep this result. So now let's look at that. So again, let's imagine that we have two particles where we have particle 1 and particle 2. We have some origin, R1 and R2. And now we want to choose another reference frame. So suppose that we pick a second reference frame, which has maybe some origin over here. And we have the vectors R1 prime and R2 prime, and the relative vector from the center of one reference frame to the center of the other reference frame. So what we have are the two conditions that R1 is equal to capital R plus R1 prime. R1 is capital R plus R1 prime. R2 is capital R plus R2 prime. And now, if we subtract these two equations, we have R1 minus R2 equals R1 prime minus R2 prime. And this shows us that the relative position vectors, and let's draw that this one, from 2 to 1. And even in our diagram, we can see that the vector from 2 to 1 does not depend on the choice of reference frame. And even more importantly, when we differentiate, we get that v1 minus v2 is equal to v1 prime minus v2 prime. And that becomes our statement that the relative velocity vector is independent of the choice of reference frame. Let's examine the velocities of an object in the center of mass reference frame. So we have object 1 and object 2, and we have Cm, and we have R1 prime, and we have R2 prime. And recall that we found that the position vector, R1 prime, was equal to the reduced mass over mu m1 times the relative position vector, R12. I'll draw that up here, R12 from 2 to 1. And just to remind you, R1 minus R2. And likewise, the position vector R2 prime is minus mu m2 over R12. Well, now we can differentiate the positions in the center of mass frame, and we find that v1, which is, of course, the derivative of the position, is just mu over m1 v12, and v2 prime is equal to mu over m2 with a minus sign v12. Now, the significance of this result is that the velocity of the object in the center of mass frame is equal to some constant times the relative velocity. Likewise, velocity v2 prime in the center of mass frame is also proportional to a constant, and it's in minus the relative velocities. So the significance of this result is that when we looked at an elastic one-dimensional collision, we already have the result that the relative velocities, v12 initial, is minus the final relative velocity. And we also know from what we saw that the relative velocity is independent of the reference frame. So this condition about relative velocity is true in any reference frame, and in particular, it's true in the center of mass frame. So what that shows us is that this condition, the statement, is that the magnitude of the relative velocity is constant. And the conclusion is because in the center of mass frame, v1 prime is proportional to the relative velocity. That tells us that in a center of mass reference frame, that the initial velocity of object 1 in the center of mass frame is equal to the final velocity of object 1. So the quantity, the speed of objects 1 and objects 2 in an elastic collision in the center of mass reference frame do not change magnitude. We can call this quantity v1 prime, and likewise v prime 2 initial is equal to v2 final prime, v2 prime, and this will make our analysis of collisions in the center of mass reference frame very easy. Two objects, when they're colliding in the center of mass reference frame, their speeds do not change. Only the direction of their velocities change.